Welcome to the Explainer. Okay, today we're diving into something completely fascinating, the invisible rules that dictate why, well, literally everything in the universe happens the way it does. We're going to unpack the delicate balance of Gibbs energy, spontaneity, and chemical equilibrium. Let's jump right in.
Section 1, The Mystery of Reversible Reactions. Let's take a quick trip back in time to a pretty surprising historical discovery.
Picture this. It's 1798 and Napoleon Bonaparte's expedition to Egypt is officially underway. But, this wasn't just your standard military campaign. Napoleon actually brought along a team of scientific advisors, and they ended up stumbling onto a massive chemical anomaly right there in the extreme environment of the Egyptian desert.
Right, so one of those key advisors was the famous French chemist Claude-Louis Berthollet. While he was out there, he noticed these thick deposits of sodium carbonate forming around the edges of some salt lakes. Now, this was huge. Back in the lab, under totally normal conditions, the chemical reaction involving these specific compounds was thought to only go one way, a one-way street to completion that actually destroyed sodium carbonate. But looking at these lakes evaporating in the harsh sun, Berthollet had a massive realization. The immense concentration of salt was actually forcing that exact reaction to run backward. He completely shattered the existing belief that chemical reactions were strictly one way.
This whole thing brilliantly illustrates what he discovered. Instead of just a single forward arrow, a reversible reaction can proceed in both directions, which we denote with those double half arrows. It can swing from left to right or right to left, depending entirely on the conditions. But that sets up a massive question for us, right? If a reaction can go forward and backward, what actually decides its final destination?
Section 2, Enthalpy, Entropy, and Spontaneity. To answer that big question, we really need to look at the fundamental physical forces at play here to find the rule that determines which way a reaction naturally wants to go.
So, we all know the first law of thermodynamics, right? It tells us that total energy is always conserved. But honestly, it has a pretty serious limitation. Energy conservation totally fails to explain why a river only naturally flows downhill. I mean, technically, it could flow uphill and still conserve total energy by perfectly swapping kinetic energy for potential energy. But our everyday experience tells us that just doesn't happen, right? The first law tells us absolutely nothing about the directionality or the spontaneity of a process.
Because of that, we have to look at the two great drivers of nature. On one hand, we've got enthalpy. Chemical systems have this intrinsic drive to lower their internal energy by releasing heat. These are your exothermic, enthalpy-driven reactions. But pulling in the exact opposite direction, we have entropy. Systems also have this profound cosmic desire for randomness and total disorder. In fact, some reactions actually absorb heat. They're endothermic, but they happen anyway simply because they create massive amounts of entropy. Think of ice melting on a warm table. It's basically a fundamental tug of war.
Which brings us to the absolutely crucial point. If enthalpy and entropy are competing, who actually wins? If a system wants to release heat but also wants to increase disorder, and those two forces are yanking the chemical reaction in entirely opposite directions, what finally determines if the reaction happens? We need a single mathematical hero to step in and resolve this conflict.
Section 3. Enter Gibbs energy. Let's look at the crucial missing piece of our thermodynamic puzzle.
Meet this truly elegant equation, Gibbs energy. Denoted by G, it equals enthalpy minus temperature times entropy. G equals H minus Ts. This specific thermodynamic property beautifully combines both the heat and the disorder into one definitive value. And what's so amazing here is that at a constant temperature and pressure, it serves as the absolute sole criterion for spontaneity. It literally judges that chemical tug-of-war for us.
Okay, let's break down exactly what that means in practice. The change in Gibbs energy, delta G, is the ultimate judge. If delta G is less than 0, meaning it's a negative number, the process is spontaneous. It happens on its own. Case closed. If delta G is greater than 0, it's non-spontaneous. No way it happens on its own. And if delta G equals exactly 0, well, the system has successfully reached equilibrium.
Section 4. Reaching dynamic equilibrium. Let's shift our focus to what actually happens when a reversible reaction finally settles down into that state of perfect balance.
This concept clears up a massive misconception. Chemical equilibrium absolutely does not mean the reaction just stops dead. Instead, the rate of the forward reaction going down and the rate of the reverse reaction going up eventually meet. They become perfectly equal. It's a dynamic state. Reactants are still forming products, and products are still breaking down into reactants, but because they're happening at the exact same speed, the overall macroscopic amounts just stop changing. Now, let's tie equilibrium back to our hero, Gibbs energy. Imagine a ball rolling down a steep hill. That curve maps out the total Gibbs energy of the mixture. A spontaneous reaction naturally keeps moving down the slope, driven by that negative delta G, moving toward lower Gibbs energy until it hits the absolute bottom of the valley. And that exact minimum point? That corresponds precisely to the equilibrium composition.
Right at the very bottom of that Gibbs energy curve, something really special happens. Delta G for any infinitesimally small change in composition becomes 0. The system is just resting at the bottom of the valley. Because delta G is 0, there's no more directional drive pulling it left toward the reactants or right toward the products. This mathematically explains perfectly why chemical equilibrium is actually achieved. Section 5. Predicting chemical destinies. So how do chemists use these exact concepts to look at a totally random mixture and predict exactly what it's going to do next?
We do this by comparing two vital metrics, Q and K. Q is the reaction quotient. Basically, it represents where we are right now in our mixture. K is the equilibrium constant, which is where we want to be, the bottom of the hill. It acts perfectly as a compass. If Q is less than K, we're too far to the left, so the reaction proceeds forward. If Q is greater than K, oops, we overshot, and the reaction spontaneously proceeds in reverse. And if Q equals K, boom, we're perfectly balanced at the bottom of the hill at equilibrium.
But wait, how do we actually know where the bottom of the hill is for any given reaction? Well, we find it by looking at the standard Gibbs energy change, or delta G0. By comparing the standard Gibbs energy of the pure products on the right to the pure reactants on the left, we can calculate exactly where that valley floor, that lowest minimum point, will sit on the curve between them.
So the final takeaway here is exactly this. If that standard Gibbs energy change, delta G0, is negative, the equilibrium shifts heavily to the right, heavily favoring the products. If it's positive, the equilibrium sits to the left, favoring the reactants. This one standard value allows chemists to predict the ultimate destiny and final composition of any chemical system. We can predict if a spontaneous reaction actually goes all the way to completion literally before we even mix a single chemical. It's a real game changer.
Which leaves us with a pretty incredible, mind-expanding thought to wrap up today's explainer. If every single chemical reaction, from those salt lakes in Egypt to the tiny cells in your own body, is just spontaneously seeking its lowest Gibbs energy, its own perfect state of balance, is the universe itself just one giant, incredibly slow reaction rolling down its own Gibbs energy curve toward ultimate equilibrium? Definitely think about that grand scale the next time you see ice melt or a fire burn. Thanks so much for exploring this with me, and keep questioning the invisible rules around you.